Hello, everybody. I'm Paulo Pagliari. I am a nutrient management specialist with the University of Minnesota Extension, and I am housed at the Southwest Research and Outreach Center at Lamberton. And today I'll be talking with you about a project that we are doing where we are monitoring the amount of nitrogen that has been coming down with the rainfall throughout the state. It's a project that was funded by the Minnesota Department of Agriculture within their FRAC division, the fertilizer checkoff portion of the MDA. And we've been very fortunate to get funding to do this monitoring for the last 2 years. And now we got funded again to continue the trial in 2021. So I hope you enjoyed this presentation, and remember that we will be hosting a live Q&A session on February the 9th. I believe this session is going to start around 11 or a bit later after 11. So please check to make sure that you have the right time for when we will have our Q&A section. So let me start by sharing my screen so we can all look at the presentation. Okay. Again, the title for this talk is Atmospheric Deposition of Nutrients. Okay, if I can get the slides, there we go. This picture here, we are looking at different precipitation patterns throughout the states since 1891 to 2010. And we can see that the red colored areas are lower precipitation, and then the blue and purple areas are where we have high precipitation. And what we can see is that the amount of precipitation is increasing from southeast to northwest as we come into 2010. And I'm pretty sure that if we were to make another one for 2020, things would be looking a little bit different already. Okay, now here we are looking at rainfall total for the year in inches for 2015-16, I'm sorry. And then this is the total for every week, except in March, where we did a 2-week sum for the first half of the month and the second half of the month. And then we go in April the same, but then we go on a weekly basis all the way until September, the end of September. We have here this black line. This is our 35 average cumulative precipitation. And then there's the yellow golden line here. We have our 2016 cumulative rainfall totals. And the one thing we can see is that early in the season, in the spring, all the way until the end of May, the amount of precipitation was very similar between the historic average and the 2016 growing season. But then as we get into early summer, midsummer, we see there's a spike in rainfall, especially in July. Here we have some pretty decent amount of rainfall that came. And that elevated the amount of rainfall, the cumulative rainfall. And then by the end of the season, we were at about 8 inches more than the average. Now, when we look at 2017, we started out a little bit higher. This would be about 2 inches higher early in the spring. But then it kind of tended to be slightly higher. But as we got to the end of the season, it pretty much there was hardly any significant difference there, maybe an inch or so. And then when you go to 2018, we can see that there is little differences in early in the spring, just like in the 2017 data. But then as you get into that early summer and late summer months, we have this spike in rainfall here in June, July. And then at the very end of the season, again, we had another big spike and ended up with an extra 11 inches of rain in 2018. For 2019, and I forgot to mention, I'm focusing here on the Lamberton location because if I were to show everything it would be a bit of a longer presentation, and we want to keep this short so you can watch many before the live session. So we're going to focus on Lamberton, but then you can ask me about the other locations during the live presentation if you have interest. 2019 was a little different. We had this big spike early in the season that we started the season already with an extra 10 inches of moisture compared to the long-term average. And then as we go on to the season, there was more later in the season rainfall, but there was also this early in the summer, midsummer rain events as we've been seeing. That helped bring the end of the season to a 15 inches additional rainfall compared to the long-term average. Now, 2020 was the opposite. We started really dry, and we pretty much stayed dry compared to the long-term average here. We started out in the early spring at about 5 inches below the long-term average, and in the late season we were about 4 inches below the long-term average. Now, to get it into perspective, how much more, how much less rainfall are we really getting throughout the growing season? To give an idea here, early in the spring, we are seeing anywhere from no increase at all or a reduction all the way to over 100% compared to the long-term average. And when we look at the yearly delta rainfall or the yearly difference, we are seeing some pretty positive increases by the end of the season, though there are some years where we see a decrease or we see equivalent to the long-term average. But in 3 out of 5 years, we saw increased rainfall precipitation. 1 year we saw the same, and 1 year we saw a decrease. So the likelihood is that we will get more above average amount of rainfall coming down compared to long-term average. So it's getting wetter for sure. Now I presented to you mostly the rainfall. I did not include the snow in there. Here I have a plot and a table with the snow, the cumulative snow for the seasons. Now this plot here is the snowfall in inches, and this is a 5-year running average. So for example, here I have the average from 1960 to 1965, and then the next one is from 65 to 70, and then 70 to 75, all the way to 220, which would be the average from 2015 to 2020. And what we see basically is that there is a upward trend for increased snowfall. Because before the 2000s, there was hardly anything above the 40-inch, with this one exception here, late in the 80s. There seems to be a lot of snow that fell in those years. But after 1995 or so, we don't really see anything below 40 inches. So you can see that even the snowfall is also showing an increase. Now, when you look at the total snow accumulation and you compare to the long-term average, very similar data to the rainfall. 3 out of the 5 years, we see higher rainfall, snowfall deposition than long-term average. 1 year was about the same, and 1 year was below the average. So on a 5-year, we can easily say here that there is about an average of 40% higher snowfall accumulation compared to a long-term average. So, but what's important about this? What is in this rainfall and the snowfall? What makes up the stuff in the water or in the snow? So basically, whatever is suspended in the atmosphere will wash down and will come down with the rain or the snow. If it's good, it will come down. If it's bad, it will come down. For example, pollution, we're going to track all that pollution back down. Herbicide drift will come down. Dust particles. I don't know if any of you remember 2 years ago that we have all that colorful snow. We're able to get some pictures. You can see that it was really dirty, and it was a day when it was not, it wasn't really windy, so it's not dust from Minnesota. Minnesota doesn't have this color of soil. They were saying there was dust from Texas that flew up here with a snowstorm, and when it snowed, all that dust came down with the snow. So just as an example that everything that is in the atmosphere will come down when it rains or it snows. But what about the nutrient? Is there any value in the nutrient that is coming down? Well, that's why we decided to do this research. We wanted to see what is coming down, what is the value, do we need to worry about it, do we need to make any modifications to the nutrients we are applying. So we are collecting rainfall and snowfall from every single event that happens throughout the year. And we have set 5 locations in Minnesota. 2019 was Lamberton, Waseca, Becker, Morris, and Crookston. There will be a graph coming up that will show you the locations more specifically. It will be easier for you to locate where they are and see why we select them. So we are measuring nitrate and ammonium to get an amount of total nitrogen coming down. We're also monitoring sulfate and rainfall and snow pH. And then in 2020, we also going to be measuring other metals like calcium, potassium, aluminum, and other particulates in the snow to try to determine what makes up most of the particulate that is in this rainfall. Again, as I mentioned, the MDA, AFREC are funding this research for 3 years. We already got 19 and 20, most of the data from 2020 collected. The 2020 season goes until the end of March, so we're still collecting samples. And then April 1st, we start the 2021 season. So here are the locations. There's a change here. In 2020, we selected the Cloquet Forest Center as a location, and we dropped Morris. Morris was very similar to what we were seeing at Lamberton, and we wanted to have a forested area to see what are the differences between agricultural areas and forested areas to see if there is any difference in what's coming down. Okay, so for our locations, then we have Waseca, that is this heavier rainfall location. And then Lamberton and Becker are this gradient where we're seeing a little bit less, but there are different properties for these 2 locations. And then the Cloquet Forest Center, which is the forested area. And then we also have Crookston as another collaborating site where it's a much lower rainfall pattern. So with this tracking, we're pretty confident that we're getting a pretty good estimate of what's coming down throughout the entire state. Now let's take a look at some of the parameters that we are measuring. Here we have rainfall pH as a function of total rainfall in inches. And the pH is on our y-axis, and the amount of rainfall is on our x-axis. I have 2 bars here. I have a yellow bar and a red bar here. The yellow bar is what the rainfall pH should be. Just natural pristine rainfall would have a pH of about 5.6. And then down here, we have the acid rainfall, when you have a lot of pollution, a lot of nitrous oxide in the atmosphere, a lot of carbonation that will react to the water, a lot of sulfates, and it will create some acids, which will drop the pH of the rainfall in the snow to very acidic conditions. And then we're looking at the data for Lamberton, Crookston, Waseca, and Becker. Now, each point here is going to be each single event that was either rain or snowfall. And you see that some locations are heavier than others. It's because of the samples that we have received and what we've been able to analyze and whatnot. So the first thing that is striking is the pH of this material, of our rainfall right now. We were expecting to see everything around 5.5, 5.6 here, which is the pristine rainfall. But for every location, the rainfall is extremely alkaline. And in particular for Lamberton, there was only 1 event that was in their range that we would expect. For Waseca, there was maybe 2 or 3 events. Becker had much more, and Crookston had a few more as well. And interesting enough is that there are some coal power plants located closer to these two locations, which could be creating the conditions for more acidic rainfall to come down. But in any event, you can see that the majority of the points are in this alkaline range. And in fact, when you look at this pH here, this is almost like seawater pH. So it's very, very, very alkaline. Another interesting result that is very clear here in Waseca is how the pH changes as a function of the amount of rainfall that comes down. It tends to be more acidic as more rain comes down, which means that probably whatever is suspended in the atmosphere, maybe some pollution, maybe a combination of things, is making the conditions to be very conducive to be alkaline. We've been watching that California is having a lot of wildfires. A lot of our rain events come from California, from the system coming from the west. It could be that a lot of that smoke is carrying a lot of ash materials that would make the precipitation be alkaline. And that's why we want to measure other minerals like aluminum, calcium, magnesium, because that would help us identify if it's actually ash that is making this material, this rainfall, more alkaline than it should be. Now, a little bit of an emphasization here on how the rainfall works. What makes up the aerosols or the particulates in atmosphere is mostly combustion of fossil fuels, right? You have engine burning oil and gasoline and diesel. Then you have power plants burning coal, and then you have sulfates and nitrous oxide being emitted to the atmosphere, and that will react with the clouds and will make your acids. And then when it comes down, you would expect to see those acids. And again, as I mentioned, pristine normal rainfall according to the EPA guidelines should be about 5.6. Whereas acid rain is usually between 4.2 to 4.4. And when we look at our pH for our areas, we see this very alkaline. So some things going on there. Now switching gears, talking about nitrate. Here, the top two graphs, I have nitrate in a y-axis as a function of each rain event during the growing season. And then ammonium as a function of each rain event. And again, those are for Lamberton. Now on the lower graph to the left, I have ammonium as a function of total rainfall, or in other words, the amount of ammonium as a function of the amount of rain that came down, and also the rainfall by date, or in other words, how much rain came down at each single event at Lamberton. The first thing that I found very interesting here is the shape in the nitrate depositions here, that we see that there's almost this bell-shaped curve where not much early in the season, then it increases during the growing season, then you get late summer, it decreases, and then by fall, hardly any nitrates coming down in the rainfall. The ammonium is a little different. It tends to be higher early in the spring, and then it comes down, and then by the midsummer to the end of summer, there's little ammonium coming down. And I think what's happening here is perhaps some of this ammonium is coming down as the soil starts to thaw and the microbes starts to be more active. A lot of nitrogen is being applied to crops, either in the fall that stays in the soil, and then as the spring comes in, that starts to move, or even fertilizer being applied in that same spring that is also moving as the soil warms up, and some of it is being lost to the atmosphere, and we know that that happens. Now, interesting also is when we look at the ammonium concentration per volume of rainfall, we can see here that anytime when the rainfall was less than 1.5 inches, there tended to be more ammonium in the rainfall. And then when you get to higher events, there was less. Of course, there's only 2 points that were higher than 1.5 inch. But you will see for other locations that seems to be the case, where it appears that there is a certain amount of material in the atmosphere that gets washed out by a certain amount of rainfall, and this certain amount changes by location. And Lamberton was about 1.5. And then here, the rainfall in each single rain event, we only had 2 higher than 1.5, but we had several between 1 and 1.5. The majority was less than 1 inch, and it was pretty well distributed throughout the season for Lamberton. Now for Crookston, a little different results observed. Ammonium and nitrate both tended to be higher early in the season and dropped off later in the season. But the nitrate, the ammonium deposition per amount of rainfall was pretty similar to Lamberton. Anything less than 1.5 had higher concentrations, but above 1.5 we saw very low concentrations. In the Crookston, there was only this isolated rainfall event that was more than 3 inches, but most cases was between a tenth to an inch and a half. There was a few events between 1 inch and an inch and a half, but the majority was less than 1 inch. For Waseca, the Waseca is really, really good. We also see a little bit higher nitrate throughout the season and lower later in the season and very early in the season, similar to Lamberton. Ammonium, again, it's higher earlier in the season, and by the midsummer it drops off and then it stays very low. The rainfall is very similar to Lamberton, with one exception. Here it seems that the limit is 1 inch. Whenever it rains more than 1 inch, it seems to wash off everything that is in the atmosphere. As you can see here, that anything below 1 inch was pretty much concentrated, and above 1 inch was more diluted in terms of the ammonium concentration per liter. And in terms of rainfall distribution, again, there was, I think, was the location with the most well-distributed rainfall in terms of large events and small events throughout the season. And again, this is a site with the highest amount of rainfall that we observed during the study. So a couple summaries. So in 2019, we saw that the amount of nitrogen being deposited varied by location. Becker was found to have the highest nitrogen deposition at about 13 pounds per acre, and Crookston had the lowest at about 3 pounds per acre. The 2020 data we are still analyzing, but we are seeing that similar results will be observed between 2020 and 2019. As I mentioned, we also measuring sulfur in these precipitations, and in 2019, the amount of sulfur was very similar to the amount of nitrogen that came down. And we're going to be measuring other minerals as well to try to determine whether or not ash could be what's causing this alkaline pH in the rainfall. And again, those are the locations, and you can see that we're trying to be as representative of the state as we can be. Of course, having another location up here would really be good, but it's very hard to, and very labor intense to collect all those rainfall events and ship it to us in a timely manner that we can have everything analyzed in a timely fashion, and so that the samples don't go to waste. And again, thank you. And if there is any questions, please write it down. And remember that on February 9th, there's going to be a live Q&A session. And I hope to see you there. Hope you have some interesting questions so that we can continue some conversation with this study. Thank you very much for participating in the Nitrogen Conference this year. And it's unfortunate that we cannot be present in person, but we're doing our best to bring you all this information that we have on an online form, and hope that you appreciate that as well. Thank you very much. All right, everybody, thank you. And again, join us for the live Q&A session. Thank you.